Taking a look at writing and balancing chemical equations here. So there's 5 types of reaction: formation, decomposition, hydrocarbon combustion, single replacement, and double replacement. So some things about each of these reactions. In a formation reaction, you have 2 or more elements or very simple compounds that combine together to make a single product. So in the question, it might say formed, or there may be multiple elemental reactants. Again, those are the things that we start with. A decomposition reaction is when one compound, the reactant, is broken down into the elements it's composed of or smaller compounds. So look for the word decomposed having only one reactant, or heated in the absence of oxygen. If it has oxygen, it may be hydrocarbon combustion. So without oxygen, it is only going to be able to be a decomposition reaction. Hydrocarbon combustion is when a hydrocarbon, so something that contains hydrogen, carbon, maybe some oxygen, and oxygen react to form carbon dioxide and water vapor. That is always the form of the reaction. So we will have some reactant plus oxygen as a gas, making CO2 as a gas and water as a gas. If you're unsure as to what water's state is, remember, fire is hot, it's going to be a gas. The only thing that changes here is what the reactant is and how we balance. The rest stays the same. For a single replacement reaction, we have one ionic compound reacted with an element, and then either the metals or the non-metals, whatever kind of element it's being reacted with, switch places. So a single replacement, look for one ionic compound reacting with an element. This ionic compound can also be an acid. Can't be molecular, but it could be an acidic compound as well. And a double replacement is when 2 ionic compounds and or acids react. The metals or the positive ions switch places. So let's see these in action. We're going to identify the type of reaction here. So in this, it's very important to recognize where our chemical reaction arrow is in each of these reactions. Remember that everything on the left of the arrow is our reactant, and everything on the right is our product. All right. So in our first one here, we have zinc and sulfur reacting. Zinc is an element, and sulfur is an element. And they've come together and they've made one product. Elements coming together to combine and make one thing is a formation reaction. In our second reaction here, we have C12H22O11 as my only reactant. So there's one reactant, and it splits into carbon, which is an element, hydrogen, which is an element, and oxygen, which is an element. So we have one reactant splitting into elements. This is a decomposition reaction. Decomposition. Ethane, C2H6, as a part of natural gas, is burned in the home. The fact that it is burned and we have a hydrocarbon leads me to believe this is combustion or hydrocarbon combustion. The next reaction here, we have Na, which is a solid, so element, and water, which is technically a molecular compound, but it can look like an acid. I know that it seems weird to think about, but hydrogen mixed with other compounds like H2S or HCl, these are acids. So what's going to happen is these are going to switch places, the positive elements. Now hydrogen is the positive here. So we would have sodium mixing with oxygen and hydrogen on its own. Now I have not balanced this for charge or for elements yet, but just the idea is here. We have an element and an acid reacting. An element and an acid reacting is a single replacement. And last but not least here, a solution of nickel 2 nitrate. We could write the formula for that. NiNO3 2. And it's a solution, so its state is aqueous, is added to a solution of sodium hydroxide. So in this case, we have an ionic compound and another ionic compound. Two ionic compounds reacting together to make some sort of product is a double replacement. So balance the following, just taking a look at elements. There's a few ways to go about balancing. What we can do, and what I typically do, is I just move left to right across my reaction. So I'm going to start with the very first element listed, and I'm just going to balance it on both sides of the reaction, and then I'm going to move to the next element. So zinc, there is currently one zinc atom here and one zinc atom here. So it appears that there is one zinc in my reactants, one in my products. It's balanced. So I'll move to the next element. S8. That means there are 8 sulfurs in my reactants. In my products, I currently only have 1 sulfur. When I'm balancing chemical reactions, I can only put numbers out front. I'm going to need 8 zinc sulfides to balance this 8 from sulfur in our reactants. But that helped to balance sulfur. But now it changed the number of zincs that I have in my products. So I now have 8 zincs in my products, but only 1 in my reactants. So I need to add an 8 in front of zinc here. To double check, you can always make a table. We're going to list all of the elements in our reactants. So we have zinc as an element here and sulfur. Currently, in my reactants, I have 8 zinc. In my products, I also have, remember, we multiply 8 zincs. There is 1 in this compound, so 8 times 1 is 8. In my reactants, I had 8 sulfurs. In my products, we have 8 zinc sulfides, so 8 times 1 again here is 8. Because each element has the same number of atoms on both the reactants and product side, this is balanced. So you can make a table to check your work if you'd like. All right, let's go to our next one here. I'm just going to start with the very first element here. Carbon. There are 12 carbons in my reactants. Just making sure that you know where your reactants and where your products are. Okay, sometimes it's hard to remember where that arrow is. 12 carbons in my reactants. I need 12 in my products. There's currently only 1. Therefore, I need to put a 12 here. That took care of carbon. So we're going to move on to hydrogen. There are 22 hydrogens in my reactants. In my products, hydrogen come in pairs. To get 22 hydrogens, when they are working in pairs, I need 11 hydrogens. 11 times 2 is 22. So that looks good. Last but not least, oxygen. I have 11 oxygens in my reactants. So I'm going to look at my products. Oxygens are in pairs. There's no way to get 11 oxygens in pairs when I want to write a whole number here. Because I'm going to have 2, 4, 6, 8, 10, or 12 in the fact that they come in twos. So because I have this odd number and oxygens only come in pairs, there's a trick to be done here. I need to double my reactant. When I do this, it changes all of the numbers of how many each element is present. So what I'm going to do is I am going to go back and I'm going to start again. All right. I know that this seems like a lot of work. There are very few instances where you have to do this. Okay. So we are no longer totally balanced. And I'm just going to leave my numbers in here so we can see what they were to begin with. Now I have 2 times 12 carbons. That means there's 24 carbons to be balanced. Carbons are singular. They come in ones. So I don't need 12. I need 24 of them. Now we're going to look at hydrogen. 22 times 2 is 44. To get 44 hydrogens when they come in pairs, I need 22 hydrogen molecules. That balances my hydrogen, and we've taken care of carbon. Last but not least, oxygen. There are 22 oxygen atoms in my reactants. To get 22 oxygen atoms in my products, I need 11 oxygen molecules. Notice how once I got here and I decided I needed to double, it just simply doubled the coefficient that I had balanced for everybody else at this point. So my final answer was 2C12H22O11 makes 24 carbons, 22 hydrogens, and 11 oxygens. That one was tricky. Writing from words. There's a few things that we need to remember. Don't forget states when you're writing a balanced chemical equation. We don't just need to balance the the compounds and the atoms within. We need to include states to describe how these elements came together. So on your periodic table, states of elements at SATP are determined by the color of the elemental symbol. Okay, so solids, all of their symbols are black on our Nelson periodic table. Liquids are listed as blue, and gases are listed as red. There's one other state to mention, aqueous. Aqueous is not a state that elements exist in. Aqueous means that something is dissolved in water. Okay, it can be listed as in solution or a solution of. When something's aqueous, it is listed as AQ. Remember, liquid, we will write an L, gases a little g, solids a little s. We typically use a little bit of a cursive L for liquids just to differentiate it from an I or anything like that. When an element is written on its own in a chemical reaction, you do need to consider homonuclear elements. This includes diatomics. So it's just a fancy word for diatonics and elements that exist in multiples. So this mnemonic below can help you remember these elements. P.S. Brinkelhoff is how I would say this. What we know about Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine all exist in nature as diatomics. So when I write just the element oxygen on its own, I've always included a 2 beside it, meaning that oxygen comes in pairs. Phosphorus and sulfur are a little bit larger. That's why I didn't just write considering diatomic elements, because they are not diatomic, di meaning 2. Phosphorus comes in 4s, and sulfur comes in 8s. I remember this because if you're drawing an S and you continued on, you become an 8. And I don't know, P and 4 are somewhat similar in their shape. So I remember that P is a 4 and S is an 8 and the rest are 2s, just by that little trick. So write and balance the word equations. We've seen these ones before. Ethane, C2H6 as a gas, is part of natural gas and is burned in the home. Burned meaning combustion. So we want to try and identify what kind of reaction we're working with here. So you can either write out all of your reactants first or determine the type of reaction. So ethane is C2H6 and it's a gas. Combustion reactions follow the exact same formula from here. I've got my hydrocarbon. Now it reacts with oxygen and it will always produce the same products, CO2 as a gas and water as a vapor, so a gas. Now that I have the skeleton of my reaction, I have two options from here. I can balance or I can write the states, and I've already done the states, so that's okay. Our next step is simply to balance the chemical equation. So, starting with our very first element, we have C. We have 2 carbons in our reactants. So we're going to balance our products by making sure there are 2 carbons in our products. The only place that carbon exists in my product is in carbon dioxide. So I need to have 2 carbon dioxides to balance carbon. Next up, we need to balance our hydrogens. There are 6 hydrogen reactants. Hydrogen is found in our water molecule in our products. So to balance for hydrogen, I need to put a 3 in front of my water molecule. Last step is to balance for oxygen. We need to add up all of the oxygens in our products to balance our oxygen in our reactants because there are 2 reactants of oxygen, but lots of products. So I have 2 times 2 oxygens, there are 4 oxygens here. 3 times 1, there are 3 oxygens coming from water. When I add these up, they add to 7. Here's where our problem exists again. If I have an odd number of oxygens that can only be balanced with a diatomic or in pairs, I need to go back and double my hydrocarbon. So that changes all of our numbers. We now have 4 carbons. To balance for 4 carbons, I need 4 CO2s. To balance for hydrogens, I now have 12 hydrogens. That means I'm going to need 6 waters. Notice again how by doubling my original hydrocarbon, I simply double the coefficients of those that I've balanced already. Now, let's take a look and decide how many oxygens we have total. We now have 4 times 2, which is 8, and 6 times 1, which is 6. 8 and 6 is 14. 14 can be balanced by something that comes in pairs. I need 7 oxygens balance. To double check at the end, identify that you have states and you have a balanced equation. There's one other thing we need to consider. So let's take a look at the next equation. A solution of nickel 2 nitrate is added to a solution of sodium hydroxide. Nickel and nitrate come together. Lots of us would stop here. We've written the formula for nickel nitrate. However, we have not considered to balance for charge. Remember, the nickel 2 nitrate is an ionic compound. When we write their formulas, we need to consider the charges of their atoms, or their ions, Nickel, it says, is a 2+ here. Nitrate is a 1-. I need 2 nitrates to balance the charge of nickel. So before we really get started in balancing, you need to balance for charge in ionic or acidic compounds. Okay, so we're going to write the rest of our equation here. Nickel 2 nitrate is reacted with sodium hydroxide. Sodium, again, is a 1+. Hydroxide is a 1-. So 1 and 1 will balance. We need to predict our products in this case. So this is a double replacement reaction. It's a double replacement because I have 2 ionic compounds reacting together. So this one's a double replacement. That means our positive ions are going to switch spots. So nickel is our positive ion in nickel nitrate, and sodium is our positive ion in sodium hydroxide. They're going to switch. So I'll rewrite our products as sodium with nitrate and nickel with hydroxide. Now I've written two new ionic formulas. I need to consider balancing them for charge. Remember, sodium was positive, nitrate was negative. 1 and 1 will balance. So sodium nitrate, as I've written it here, is currently balanced for charge. Nickel, remember, is nickel 2 plus in this case, and hydroxide is a -1. I'm going to need 2 hydroxides to balance the charge for nickel. We have balanced for charge in ionic and acidic compounds in both our reactants and products. We can check that off. Next, let's add states. Nickel 2 nitrate is added to a solution. A solution of nickel 2 nitrate. That means that nickel 2 nitrate here is aqueous. It's added to a solution of sodium hydroxide. That means that sodium hydroxide is also aqueous. We've now decided that we have a reaction happening in a beaker in water. We have our nickel nitrate and we have our sodium hydroxide. Any products that are created from this reaction will also still be in this water. Because they are in water, we need to decide if these new ionic substances are soluble or insoluble in water. This is where our solubility table comes in handy. So sodium nitrate is our first one. Let's look up the solubility of sodium nitrate. Because sodium nitrate is created in this water, let's see if it's going to dissolve in this water. Nitrate is in the first column of your solubility table on the back of your periodic table. Most things are soluble with nitrate. If we look to the things that are insoluble, sodium nitrate is not listed there. Therefore, sodium nitrate is aqueous. It is soluble in the water it is produced in. Nickel 2 hydroxide. Looking at hydroxide, there are a list of ions that are soluble with hydroxide. Nickel 2 plus is not listed as one of them. Therefore, nickel 2 plus with hydroxide is not soluble. That means that when it is created in an aqueous environment, it will not dissolve and it will precipitate to the bottom as a solid. We've added states to our reaction. Our last step is to balance. Starting with nickel. We have 1 nickel atom on this side and 1 nickel atom on this side. Nickel is balanced. Rather than considering each element in the nitrate ion, nitrogen and oxygen, I can see that it moves together. So let's consider nitrate as a grouping together. In our reactants, we have 2 nitrate ions, polyatomic ions. In our products, we only have 1. Therefore, to balance for this, I need to put a 2 out front. Remember, I've already balanced for charge, so I don't want to add any more subscripts here. The balancing for atoms is always out front. Moving on to my next element, I've got 1 sodium here and 2 sodiums in our products. Remember, we need to multiply by the coefficient now, and there's only 1 sodium in this compound. So to balance for sodiums, I need to put a 2 in front of NaOH. I now have 2 sodiums on each side. However, I also have 2 hydroxides in my reactants now. Let's double check our products. In our products, I have 2 hydroxides. There's no number out front here, so I don't need to multiply it by anything. It appears that everything is balanced. Again, if you're unsure, you can always make a table where you list your elements present, we check the number of them in our reactants, and we check the number of them in our products. Just be careful because some elements exist in multiple compounds. We find oxygen here and in our second reactant. We find oxygen in both products as well. So you need to add up the total number of oxygens in each side. Don't forget. There's lots of practice for this in your booklet. There's also an extra practice worksheet if you really need some extras. Take a look at it and be sure that you're comfortable. This is something that we do at the beginning of a lot of questions later in our course, and it is something that I expect you become very familiar with and can do quickly and easily.